Picture this, a vast cosmic neighborhood, home to thousands of galaxies, each one a swirling island of stars, gas, and dust. Now imagine that within this bustling galactic metropolis, there are secrets so profound, so baffling, that even the brightest minds in science are left scratching their heads. Welcome to the Virgo Cluster, the largest galaxy cluster in our cosmic backyard, and a treasure trove of mysteries waiting to be unraveled. From galaxies that defy the laws of physics to black holes that spit out jets of energy stretching millions of light years, the Virgo Cluster is a place where the universe seems to play by its own rules. In this video, we're diving deep into 25 of the most unexplained phenomena lurking within this cosmic enigma. What causes galaxies to lose their dark matter? Why are there ghostly clouds of gas floating between galaxies? And what secrets do the cluster's supermassive black holes hold? By the end of this journey, you'll not only uncover the strange and wondrous truths of the Virgo Cluster, but also see the universe in a whole new light. So, buckle up, this is one cosmic adventure you won't want to miss. Now, let's zoom in on one of the most baffling mysteries in the Virgo Cluster, a galaxy that seems to have lost its dark matter. Meet NGC 1052 DF2, a galaxy that has left scientists utterly perplexed. Dark matter, the invisible substance that makes up most of the universe's mass, is supposed to be everywhere, holding galaxies together like cosmic glue. But NGC 1052 DF2 appears to be missing this crucial ingredient entirely. Discovered in 2018, this galaxy immediately stood out because its stars moved in ways that defied expectations. Normally, the gravitational pull of dark matter causes stars to orbit at certain speeds, but in NGC 1052 DF2, the stars moved far slower than predicted. This strange behavior suggested that dark matter was either absent or present in incredibly small amounts, something that shouldn't be possible according to our current understanding of galaxy formation. The discovery of NGC 1052 DF2 has sparked heated debates among astronomers. Some argue that the galaxy's unusual properties could be due to observational errors or unique conditions in its environment. Others propose that it might challenge our fundamental theories about dark matter, suggesting that there could be alternative explanations for how galaxies form and evolve. Could this galaxy be a rare exception, or is it a sign that our understanding of the universe's structure is incomplete? What makes NGC 1052 DF2 even more intriguing is its location within the Virgo Cluster. This dense region of space is filled with galaxies interacting and colliding, which could play a role in stripping away dark matter. But how exactly this process works, or if it's even possible, remains a mystery. As scientists continue to study this enigmatic galaxy, one thing is clear: NGC 1052 DF2 is forcing us to rethink what we know about the cosmos. And as we'll see next, the story of dark matter in the Virgo Cluster only gets stranger from here. Now, let's take a closer look at the theories trying to explain the baffling absence of dark matter in NGC 1052 DF2. One of the most intriguing possibilities is that our understanding of gravity itself might need a rethink. Some scientists have proposed alternative gravity theories, such as modified Newtonian dynamics, or MUND, which suggests that gravity behaves differently on cosmic scales than what Newton or Einstein predicted. If MUND is correct, it could explain why NGC 1052 DF2 stars move the way they do without the need for dark matter. However, this idea remains controversial, as it would require rewriting some of the most fundamental laws of physics. Another angle scientists are exploring is the possibility of observational errors. Could there be something about the way we're measuring NGC 1052 DF2 that's leading us astray? For instance, the galaxy's distance from Earth might be miscalculated, which could throw off our estimates of its mass and motion. Alternatively, the galaxy's unique environment within the Virgo cluster might be playing tricks on our observations. The intense gravitational interactions in this crowded region could be distorting our view, making it seem like dark matter is missing when it's actually there, just hidden in a way we don't yet understand. Then there's the idea that NGC 1052 DF2 might have lost its dark matter through some extraordinary cosmic event. Galaxies in clusters like Virgo often collide and interact, and these violent encounters could strip away dark matter over time. If NGC 1052 DF2 was once a normal galaxy with dark matter, perhaps it was stripped clean by a close encounter with another galaxy or the cluster's gravitational forces. This theory is particularly compelling because it ties the mystery of NGC 1052 DF2 to the dynamic environment of the Virgo cluster itself. But what if none of these explanations hold up? What if NGC 1052 DF2 is truly a galaxy without dark matter? This would be a groundbreaking discovery, forcing us to reconsider how galaxies form and evolve. It could mean that dark matter isn't as universal as we thought, or that there are entirely new processes at work in the universe that we haven't even imagined yet. The implications would ripple through cosmology, challenging everything from the Big Bang theory to our models of galaxy formation. As we continue to unravel the mystery of NGC 1052 DF2, one thing is certain: this galaxy is a cosmic puzzle that refuses to fit neatly into our current understanding of the universe. And as we move forward, we'll explore even more strange and unexplained phenomena in the Virgo cluster, each one adding another layer to the mystery of this fascinating region of space. Now, shifting our gaze to another cosmic marvel, let's turn our attention to the supermassive black hole at the heart of Messier 87, or M87, a galaxy that has captured the world's imagination. This black hole made history in 2019 when it became the first ever to be directly imaged, a groundbreaking achievement that brought the mysteries of these cosmic giants into sharp focus. But what makes this black hole so extraordinary? For starters, its sheer size is staggering, weighing in at around 6.5 billion times the mass of our Sun. It's one of the most massive black holes ever discovered. To put that into perspective, if our solar system were a grain of sand, this black hole would be the size of a mountain. But it's not just its size that's fascinating, it's also its behavior. The black hole at the center of M87 is an active powerhouse spewing out a jet of particles that stretches for thousands of light years. This jet, traveling at nearly the speed of light, is a testament to the immense energy generated by the black hole's gravitational pull. Yet, despite its ferocious activity, the black hole itself remains shrouded in mystery. How did it grow to such an enormous size? Did it form from the collapse of a single massive star? Or did it grow over billions of years by devouring stars, gas, and even other black holes? These questions remain unanswered, challenging our understanding of how supermassive black holes come to be. Adding to the intrigue is the black hole's environment. M87 sits in the dense core of the Virgo cluster, a region teeming with galaxies and intergalactic gas. This crowded neighborhood likely played a role in the black hole's growth, feeding it with material over eons. But the exact mechanisms behind this process are still unclear. Did the black hole grow steadily over time, or did it experience sudden bursts of growth during violent galactic collisions? And what role does the surrounding cluster play in shaping its behavior today? These are just some of the questions astronomers are racing to answer. The first image of this black hole, captured by the Event Horizon Telescope, was a monumental achievement, but it also raised new questions. For instance, why does the black hole's shadow appear lopsided? Is this due to the way light bends around it, or does it hint at something more profound about the nature of spacetime itself? As we continue to study this cosmic behemoth, one thing is clear: the supermassive black hole at the center of M87 is not just a scientific curiosity, it's a window into the deepest mysteries of the universe. And as we move forward, we'll uncover even more astonishing phenomena in the Virgo cluster, each one revealing new layers of cosmic wonder. Now, let's zoom in on one of the most striking features of M87's supermassive black hole, its colossal relativistic jet. This jet, a narrow beam of particles and radiation, stretches an astonishing 5,000 light-years into space, a distance so vast it's almost impossible to comprehend. But what exactly powers this cosmic fire hose, and why does it behave the way it does? The answer lies in the extreme physics at play near the black hole's event horizon, where gravity is so intense that even light struggles to escape. The jet originates from the black hole's accretion disk, a swirling maelstrom of gas, dust, and other matter spiraling inward at incredible speeds. As this material gets closer to the black hole, it heats up to millions of degrees, emitting intense radiation. Some of this material, instead of falling into the black hole, gets funneled along magnetic field lines and blasted outward at nearly the speed of light. This process, known as relativistic beaming, creates the jet we observe. But here's where things get even more fascinating. The jet isn't just a straight line. It twists and bends, forming intricate structures that defy our expectations. One of the biggest mysteries surrounding the jet is how it maintains its incredible energy over such vast distances. Normally, we'd expect such a beam to dissipate or spread out, but the jet from M87's black hole remains tightly focused, punching through the surrounding intergalactic medium with ease. This suggests that the black hole is not just a passive eater of matter but an active engine, converting gravitational energy into powerful outflows that shape its environment. But how exactly does this energy transfer work, and what role do the black hole's spin and magnetic fields play in this process? These are questions that continue to puzzle scientists. Adding to the intrigue is the jet's impact on the surrounding Virgo cluster. As the jet plows through the cluster's intergalactic gas, it creates shock waves and heats the surrounding material, influencing the evolution of nearby galaxies. This interaction raises another question. Could the jet be a key player in regulating star formation and galaxy growth within the cluster? Some astronomers believe so, suggesting that the jet's energy might even prevent gas from cooling and collapsing into new stars, effectively putting a brake on galaxy formation in its vicinity. The study of M87's jet isn't just about understanding one black hole, it's about unraveling the fundamental physics that govern these cosmic powerhouses. From the way they accelerate particles to near-light speeds to their ability to shape entire galaxy clusters, black hole jets challenge our understanding of energy, gravity, and the very fabric of space-time. As we continue to observe and analyze this extraordinary phenomenon, we're not just peering into the heart of M87, we're uncovering the secrets of the universe itself. And with each discovery, we're reminded that the cosmos is far stranger and more wondrous than we ever imagined. Now, let's shift our focus to a phenomenon that's as mysterious as it is beautiful, the faint, ghostly glow of intracluster light in the Virgo cluster. Unlike the bright, concentrated light of galaxies, this ethereal glow comes from stars that have been ripped away from their parent galaxies and now drift freely in the vast spaces between them. But how did these stars end up here, and what can they tell us about the Virgo cluster's turbulent past? The origins of intracluster light lie in the violent interactions between galaxies. As galaxies collide and merge within the cluster, their gravitational forces tear stars from their orbits, scattering them into the intergalactic void. Over billions of years, these stars accumulate, creating a diffuse, almost imperceptible glow that permeates the cluster. This light is incredibly faint, so faint that it's often drowned out by the brightness of galaxies themselves. Yet, with advanced telescopes and careful observation, astronomers have been able to map its distribution, revealing a cosmic tapestry of lost stars. What's truly fascinating is what this light tells us about the Virgo cluster's history. The distribution of intracluster light isn't random. It follows the paths of past galactic collisions and mergers. By studying its patterns, scientists can piece together a timeline of the cluster's evolution, uncovering the dramatic events that shaped its current structure. For instance, areas with higher concentrations of intracluster light often correspond to regions where galaxies have interacted most violently, leaving behind a trail of stellar debris. But the story doesn't end there. Intracluster light also provides clues about the cluster's dark matter distribution. Since these stars are no longer bound to any galaxy, their movements are influenced primarily by the cluster's gravitational field, which is dominated by dark matter. By tracking the motion of these stars, astronomers can infer the presence and distribution of dark matter, offering a unique window into one of the universe's greatest mysteries. This faint glow is more than just a cosmic curiosity. It's a record of the Virgo cluster's violent history and a tool for understanding its hidden structure. As we continue to study intracluster light, we're not just observing the aftermath of galactic collisions, we're uncovering the forces that have shaped the cluster over billions of years. And in doing so, we're reminded that even the faintest light can illuminate the darkest corners of the cosmos. Now, let's turn our attention to a phenomenon that challenges our understanding of galaxy formation: the enigmatic ultra-diffused galaxies found within the Virgo cluster. These galaxies are unlike anything we've come to expect from typical galaxies. They are incredibly large, often spanning sizes comparable to the Milky Way, yet they contain only a fraction of the stars. Imagine a galaxy so faint and spread out that it's almost invisible against the backdrop of space, a ghostly presence that defies conventional wisdom. Ultra-diffused galaxies were first discovered in the Virgo cluster in recent years, and their existence has left astronomers scratching their heads. Unlike the dense, star-packed galaxies we're familiar with, these galaxies are so sparse that they appear almost transparent. Their stars are spread so thinly that they emit very little light, making them incredibly difficult to detect. In fact, many of these galaxies were only spotted thanks to advanced telescopes and meticulous observation techniques. But why are they so faint, and how did they end up this way? One of the most puzzling aspects of ultra-diffuse galaxies is their lack of dark matter. Dark matter, the invisible substance that makes up most of a galaxy's mass, is thought to be essential for holding galaxies together. Yet, many ultra-diffuse galaxies seem to have very little of it, if any at all. This raises a critical question: how do these galaxies maintain their structure without the gravitational glue of dark matter? Some theories suggest that they may have lost their dark matter through interactions with other galaxies, while others propose that they formed in an entirely different way, perhaps in regions of the universe where dark matter was scarce to begin with. Another mystery lies in their star formation, or rather, the lack of it. Ultra-diffuse galaxies are remarkably quiet, with very little ongoing star formation. This is unusual, as most galaxies, even those in clusters, tend to have at least some regions where new stars are being born. The absence of star formation in these galaxies suggests that they may have exhausted their gas reserves long ago, leaving them as cosmic relics of an earlier era. But how did they lose their gas, and why haven't they replenished it over billions of years? The discovery of ultra-diffuse galaxies has opened up a new frontier in our understanding of galaxy evolution. They challenge our assumptions about how galaxies form, grow, and interact within clusters like Virgo. Are they failed galaxies that never quite came together? Or are they the remnants of larger galaxies that were stripped of their stars and gas over time? These questions remain unanswered, but they highlight the complexity and diversity of the universe. As we continue to study these ghostly galaxies, we're reminded that even in the vastness of space, there are still mysteries waiting to be uncovered. And with each discovery, we come one step closer to understanding the true nature of the cosmos. Now, shifting our focus to another cosmic puzzle, we delve into the mystery of the Virgo Cluster's missing baryons. Baryons, the building blocks of normal matter, include protons and neutrons, essentially the stuff that makes up stars, planets, and even us. Yet, when astronomers tally up the baryons in the Virgo Cluster, a significant portion seems to be missing. This discrepancy, known as the missing baryon problem, has become one of the most intriguing challenges in modern astrophysics. So, where could these baryons be hiding? One leading theory points to something called the warm-hot intergalactic medium, or WIM for short. This elusive substance is thought to exist in the vast spaces between galaxies, where it forms a diffuse web of gas that's incredibly hot, reaching temperatures of millions of degrees, but also incredibly thin. Detecting the WIM is no easy task, as it doesn't emit much light and is nearly invisible to most telescopes. However, its presence could explain where the missing baryons have gone. The WIM is believed to be a remnant of the early universe, a leftover from the cosmic web that formed as the universe expanded. Over billions of years, gravity pulled matter into dense regions, creating galaxies and clusters, while the WIM remained in the voids between them. But even though it's spread out, the WIM could contain a significant amount of the universe's baryons. The challenge lies in proving its existence. Astronomers have turned to specialized instruments such as X-ray telescopes to search for faint traces of this hot gas. While some evidence has been found, the WIM remains difficult to study in detail. Another possibility is that the missing baryons are hiding in other forms, such as cold gas clouds or even within the galaxies themselves, but in ways that are difficult to detect. For instance, some baryons might be locked up in faint, low-mass stars or in diffuse gas that doesn't emit much light. Alternatively, they could be part of the intracluster medium, the hot gas that fills the spaces between galaxies in a cluster. While this gas is easier to detect than the WIM, it still doesn't account for all the missing baryons. The missing baryon problem isn't just a curiosity, it has profound implications for our understanding of the universe. Baryons make up the visible matter we interact with every day, and if a significant portion is unaccounted for, it means our models of galaxy formation and cosmic evolution might be incomplete. Solving this mystery could help us better understand how galaxies form, how clusters evolve, and even how the universe itself is structured. As we continue to explore the Virgo Cluster and beyond, the search for these missing baryons remains a top priority. Each new observation brings us closer to uncovering their hiding places, whether in the WIM, in cold gas clouds, or in some other form we haven't yet imagined. And with every discovery, we gain a deeper appreciation for the complexity and wonder of the cosmos. The missing baryons remind us that even in the vastness of space, there are still secrets waiting to be revealed. Now, let's turn our attention to another cosmic oddity within the Virgo Cluster, the peculiar galaxy known as NGC 4388. This galaxy stands out not just for its appearance but for its strange and dynamic behavior, which has left astronomers scratching their heads. NGC 4388 is a Seyfert galaxy, a type of galaxy with an extremely bright core powered by a supermassive black hole. But what makes this galaxy truly fascinating are its unusual gas outflows and bursts of star formation, which defy typical galactic behavior. One of the most striking features of NGC 4388 is its powerful gas outflows. These outflows are streams of gas being ejected from the galaxy at incredible speeds, often reaching hundreds of kilometers per second. But here's the twist: these outflows aren't just random. They appear to be driven by the intense activity near the galaxy's supermassive black hole. As material spirals toward the black hole, it heats up and releases enormous amounts of energy, which then pushes gas outward in dramatic jets. This process, known as active galactic nucleus feedback, is common in many galaxies, but in NGC 4388, it's taken to an extreme. The outflows are so intense that they're reshaping the galaxy itself, stripping away gas that could otherwise form new stars. But that's not all. Despite these violent outflows, NGC 4388 is also experiencing bursts of star formation. This is unusual because in most galaxies, strong outflows tend to suppress star formation by removing the gas needed to create new stars. So why is NGC 4388 different? One theory suggests that the outflows might be compressing pockets of gas in certain regions, triggering star formation in localized areas. Another possibility is that the galaxy is interacting with its environment, perhaps through collisions or gravitational tugs from neighboring galaxies, which could be funneling fresh gas into the system. These interactions might be counteracting the effects of the outflows, allowing stars to form in unexpected places. Adding to the mystery, NGC 4388 also exhibits a unique structure. Observations reveal that its disk is tilted and its gas distribution is highly irregular. This asymmetry could be the result of past interactions with other galaxies or even the influence of the Virgo cluster's dense environment. The cluster's gravitational forces and the pressure from its intracluster medium might be playing a role in shaping NGC 4388's behavior, though the exact mechanisms remain unclear. The strange behavior of NGC 4388 challenges our understanding of how galaxies evolve. It shows that even in a well-studied region like the Virgo cluster, there are still surprises waiting to be uncovered. By studying this galaxy, astronomers hope to learn more about the complex interplay between supermassive black holes, gas outflows, and star formation processes that shape not just individual galaxies but the entire universe. As we continue to explore the Virgo cluster, NGC 4388 serves as a reminder that the cosmos is full of unexpected phenomena. Each discovery pushes the boundaries of our knowledge, revealing new layers of complexity in the grand tapestry of the universe. And with every observation, we come one step closer to unraveling the mysteries that lie hidden among the stars. Now, let's shift our gaze to a phenomenon that envelops the entire Virgo cluster, a vast invisible structure known as the radio halo. This colossal feature isn't something you can see with optical telescopes, but it reveals itself through radio waves, painting a picture of immense energy and activity. The radio halo is a diffuse, cloud-like region of radio emission that spans millions of light-years, surrounding the cluster like an invisible aura. But what exactly is causing this enormous structure, and what secrets does it hold about the Virgo cluster's inner workings? The origins of the radio halo are deeply tied to the cluster's dynamic environment. At the heart of the Virgo cluster, galaxies are constantly moving, colliding, and interacting with one another. These interactions generate shock waves and turbulence within the cluster's hot gas, a medium known as the intracluster medium. As these shock waves ripple through the gas, they accelerate charged particles such as electrons to nearly the speed of light. When these high-speed electrons spiral around magnetic fields, they emit radio waves, creating the faint glow we detect as the radio halo. This process, known as synchrotron radiation, is the key to understanding the halo's existence. But the radio halo isn't just a byproduct of cosmic chaos, it's also a window into the cluster's magnetic fields. The magnetic fields within the Virgo cluster are incredibly complex, weaving through the intracluster medium like invisible threads. These fields play a crucial role in shaping the radio halo, guiding the movement of charged particles and influencing the intensity and structure of the radio emission. By studying the halo, astronomers can map these magnetic fields, gaining insights into how they form, evolve, and interact with the cluster's environment. One of the most intriguing aspects of the radio halo is what it tells us about particle acceleration processes on a cosmic scale. The particles responsible for the radio emission are some of the most energetic in the universe, and their acceleration requires immense amounts of energy. This energy likely comes from the violent events occurring within the cluster, such as galaxy mergers, supernova explosions, and the activity of supermassive black holes. These events inject energy into the intracluster medium, creating the conditions needed to accelerate particles to such extreme speeds. The radio halo, therefore, serves as a record of the cluster's most energetic moments, preserving the echoes of its turbulent past. The presence of the radio halo also raises questions about the Virgo cluster's evolution. Why do some galaxy clusters have radio halos while others do not? The answer may lie in the cluster's history of mergers and interactions. Clusters that have experienced recent or ongoing mergers tend to have more pronounced radio halos, as these events generate the turbulence needed to accelerate particles. The Virgo cluster, with its rich history of galactic interactions, fits this pattern perfectly. Its radio halo is a testament to the cluster's active and dynamic nature, offering clues about how it has grown and changed over billions of years. As we explore the radio halo, we're reminded once again of the Virgo cluster's complexity. This invisible structure, born from the interplay of magnetic fields, particle acceleration, and cosmic collisions, reveals a side of the cluster that would otherwise remain hidden. It's a reminder that the universe is full of phenomena that challenge our understanding and push the boundaries of what we know. And as we continue to study the Virgo cluster's radio halo, we uncover not just the secrets of this remarkable structure, but also the forces that shape the cosmos on the grandest scales. Now, let's turn our attention to one of the most elusive and mysterious aspects of the Virgo cluster, the enigmatic dark matter filaments. These invisible threads are thought to weave through the cosmos, connecting galaxies like a vast cosmic web. While we can't see them directly, their presence is inferred through their gravitational effects on visible matter, shaping the structure of the universe on the grandest scales. But what exactly are these filaments, and why are they so difficult to detect and study? Dark matter filaments are believed to be long, thin structures composed of dark matter, the mysterious substance that makes up about 85% of the universe's total mass. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes. Instead, it reveals itself through its gravitational influence, bending the light of distant objects and affecting the motion of galaxies. In the Virgo cluster, these filaments are thought to stretch between galaxies, acting as bridges that link them together in a vast network. This cosmic web is a fundamental prediction of our current understanding of the universe, but proving its existence has been a monumental challenge. One of the primary obstacles in studying dark matter filaments is their faint and diffuse nature. Because they don't emit light, astronomers must rely on indirect methods to detect them. One such method is gravitational lensing, where the gravity of a massive object like a galaxy cluster bends the light from objects behind it. By carefully analyzing these distortions, scientists can map the distribution of dark matter, including the faint filaments that connect galaxies. However, this process is incredibly complex, requiring precise measurements and advanced computational models to separate the signal from the noise. Another challenge lies in the sheer scale of these filaments. They can stretch for millions of light years, far larger than the galaxies they connect. This vastness makes it difficult to observe them in their entirety, as they often extend beyond the field of view of even the most powerful telescopes. Additionally, the filaments are not uniform. Their density and structure can vary significantly, adding another layer of complexity to their study. Despite these challenges, astronomers have made significant strides in mapping the cosmic web, using both observations and simulations to piece together its intricate structure. The existence of dark matter filaments has profound implications for our understanding of the universe. They are thought to play a crucial role in the formation and evolution of galaxies, guiding the flow of gas and dark matter into the denser regions where galaxies form. Without these filaments, the universe as we know it might look very different. They are the scaffolding upon which the cosmos is built, shaping the distribution of matter on the largest scales. Yet, much about them remains unknown, from their exact composition to the mechanisms that govern their formation and evolution. As we continue to explore the Virgo cluster, the study of dark matter filaments offers a tantalizing glimpse into the hidden architecture of the universe. These invisible threads, though elusive, hold the key to understanding how galaxies are connected and how the cosmos has evolved over billions of years. They remind us that the universe is far more complex and interconnected than we can see with our eyes alone, and that some of its greatest mysteries are still waiting to be uncovered. Now, shifting our gaze to another fascinating mystery within the Virgo cluster, we encounter the ghostly gas clouds that drift silently between its galaxies. These ethereal clouds, composed primarily of hydrogen and other elements, are not bound to any single galaxy but instead float freely in the vast intergalactic space. Their presence is both haunting and intriguing, raising questions about their origins and their role in shaping the cluster's evolution. These gas clouds are remnants of the violent interactions that have shaped the Virgo cluster over billions of years. As galaxies collide and merge, they can strip gas from one another, ejecting it into the space between them. This process, known as ram pressure stripping, is particularly common in dense environments like the Virgo cluster, where galaxies are packed closely together. Over time, this ejected gas accumulates, forming the diffuse clouds we observe today. But how do these clouds persist in such a dynamic and chaotic environment? One key factor is the sheer size and density of the Virgo cluster itself. The gravitational pull of the cluster's immense mass helps to hold these gas clouds in place, preventing them from dissipating entirely. Additionally, the clouds are often found in regions where the gravitational forces of multiple galaxies overlap, creating a kind of cosmic tug-of-war that keeps the gas suspended in place. Despite their tenuous nature, these clouds play a crucial role in the cluster's ecosystem, acting as reservoirs of raw material for future star formation. But the story doesn't end there. These ghostly gas clouds also serve as a record of the cluster's turbulent history. By studying their composition and distribution, astronomers can piece together the sequence of events that have shaped the Virgo cluster over time. For example, the presence of heavy elements like oxygen and carbon in the clouds suggests that they were once part of galaxies where stars formed and died, enriching the gas with these elements before it was ejected into intergalactic space. This process provides a fascinating glimpse into the life cycle of galaxies and the recycling of matter on a cosmic scale. Yet, despite their importance, these gas clouds remain shrouded in mystery. Their low density makes them incredibly difficult to observe directly, requiring highly sensitive instruments and innovative techniques. One such method involves detecting the faint glow of hydrogen gas, known as the Lyman alpha emission, which can reveal the presence of these clouds even when they are otherwise invisible. Another approach uses X-ray observations to trace the hot gas that permeates the cluster, offering clues about the interactions between the gas clouds and their surroundings. The study of these ghostly gas clouds is not just an academic exercise. It has profound implications for our understanding of galaxy evolution and the large-scale structure of the universe. They remind us that the space between galaxies is far from empty, but rather a dynamic and ever-changing environment where matter is constantly being exchanged and transformed. As we continue to explore the Virgo cluster, these enigmatic clouds will undoubtedly reveal even more secrets about the cosmos, challenging our assumptions and deepening our appreciation for the complexity of the universe. With this in mind, let's now turn our attention to another intriguing phenomenon within the Virgo cluster, where the mysteries only deepen as we venture further into the cosmic unknown. Now, as we delve deeper into the cosmic tapestry of the Virgo cluster, we encounter a phenomenon that challenges our understanding of galaxy formation: the abundance of dwarf galaxies. These small, faint galaxies are scattered throughout the cluster, often orbiting larger galaxies like cosmic satellites. Despite their diminutive size, dwarf galaxies hold immense significance, offering clues about the early universe and the processes that shaped it. Yet, their very existence poses a puzzle that continues to baffle astronomers. Dwarf galaxies are thought to be the building blocks of larger galaxies, forming in the early stages of the universe and merging over time to create the massive structures we see today. In the Virgo cluster, however, there are far more dwarf galaxies than current models predict. According to the widely accepted lambda cold dark matter model, which describes the formation and evolution of the universe, we should see fewer dwarf galaxies than we actually observe. This discrepancy, known as the missing satellite problem, has become one of the most enduring mysteries in modern astrophysics. One possible explanation lies in the nature of dark matter. Dwarf galaxies are believed to be embedded in dark matter halos, which provide the gravitational scaffolding necessary for their formation. However, simulations based on the lambda cold dark matter model suggest that many of these halos should remain dark, failing to form stars and becoming invisible to our telescopes. The fact that we observe so many dwarf galaxies in the Virgo cluster implies that our understanding of dark matter or the processes of star formation within these halos may be incomplete. Another intriguing aspect of dwarf galaxies is their diversity. Some are gas-rich and actively forming stars, while others are gas-poor and appear to have exhausted their star-forming material. This variation suggests that environmental factors within the Virgo cluster play a significant role in shaping their evolution. For instance, the intense gravitational forces and interactions with larger galaxies can strip away gas from dwarf galaxies, halting star formation and leaving them as faint, ghostly remnants of their former selves. Despite their challenges, dwarf galaxies are invaluable laboratories for studying the universe. Their simple structures and relatively low masses make them ideal for testing theories of galaxy formation and evolution. By observing their distribution, composition, and interactions within the Virgo cluster, astronomers can gain insights into the conditions of the early universe and the role of dark matter in shaping cosmic structures. Yet, the mystery of dwarf galaxies remains far from solved. Why are there so many of them in the Virgo cluster? What processes allow some dark matter halos to form stars while others remain invisible? These questions continue to drive research, pushing the boundaries of our knowledge and inspiring new theories. As we explore further, the dwarf galaxies of the Virgo cluster remind us that even the smallest cosmic objects can hold the keys to understanding the grandest mysteries of the universe. With this in mind, let's now turn our attention to another enigmatic feature of the Virgo cluster, where the interplay of forces and matter continues to reveal the intricate dance of cosmic evolution. Shifting our gaze to another fascinating feature of the Virgo cluster, we encounter a phenomenon that reveals the hidden forces at work within this cosmic neighborhood, the giant X-ray cavities. These vast, bubble-like structures are carved out of the cluster's hot gas, creating voids that stretch across hundreds of thousands of light years. But what exactly are these cavities and how do they form? The answer lies in the interplay between supermassive black holes and the surrounding environment, offering a glimpse into the dynamic processes shaping the cluster. The X-ray cavities are detected through observations of the cluster's hot gas, which emits X-rays as it swirls and interacts within the gravitational pull of the Virgo cluster. These cavities appear as dark regions within the glowing gas, indicating areas where the gas has been pushed away or displaced. The most likely culprit behind these structures is the activity of supermassive black holes at the centers of galaxies within the cluster. As these black holes consume matter, they release enormous amounts of energy in the form of jets and outflows, which can blow away the surrounding gas, creating these immense cavities. One of the most striking examples of this phenomenon is found in the galaxy Messier 87, or M87, home to the famous supermassive black hole that was the first to be directly imaged. The jets emanating from this black hole are so powerful that they carve out massive cavities in the cluster's hot gas, stretching far beyond the galaxy itself. These jets not only shape the immediate environment but also influence the entire cluster, redistributing gas and energy on a colossal scale. But the story doesn't end there. The X-ray cavities also provide valuable insights into the cluster's history and evolution. By studying their size, shape, and distribution, astronomers can trace the activity of supermassive black holes over millions or even billions of years. These cavities act as cosmic fossils, preserving a record of past outbursts and interactions that have shaped the cluster's structure. Moreover, the process of gas being pushed away by these jets can trigger new star formation in surrounding regions, creating a feedback loop that influences the growth of galaxies within the cluster. The presence of X-ray cavities also highlights the role of feedback mechanisms in galaxy clusters. Without the energy injected by supermassive black holes, the hot gas in the cluster would cool and collapse, leading to runaway star formation. Instead, the cavities help regulate this process, maintaining a delicate balance that prevents the gas from cooling too quickly. This feedback is crucial for understanding how galaxy clusters evolve and why they appear as they do today. Yet, many questions remain. How exactly do the jets from supermassive black holes interact with the surrounding gas? What determines the size and shape of the cavities? And how do these structures influence the long-term evolution of the cluster? These mysteries continue to drive research, with astronomers using advanced telescopes and simulations to unravel the complex dynamics at play. As we explore the X-ray cavities of the Virgo cluster, we're reminded of the intricate connections between the smallest and largest scales in the universe. From the activity of supermassive black holes to the vast structures they create, these phenomena offer a window into the forces that shape our cosmic neighborhood. And with that, let's turn our attention to another intriguing feature of the Virgo cluster, where the mysteries of the cosmos continue to unfold. Now, let's turn our attention to a galaxy that stands out even in the crowded Virgo cluster, IC 3418. This peculiar galaxy is undergoing a dramatic transformation, one that challenges our understanding of how galaxies evolve over time. Known as ram pressure stripping, this process occurs when a galaxy moves through the dense gas of a galaxy cluster, causing its own gas to be stripped away by the sheer force of the interaction. IC 3418 is a textbook example of this phenomenon, and its unique features are providing astronomers with invaluable insights into the life cycle of galaxies. As IC 3418 hurtles through the Virgo cluster, it encounters the cluster's hot, diffuse gas, which acts like a cosmic wind. This wind exerts immense pressure on the galaxy, stripping away its gas and dust, the very materials needed to form new stars. What remains is a galaxy that appears to be losing its identity, with long, trailing streams of gas being pulled away from its main body. These streams, often referred to as tails, are a telltale sign of ram pressure stripping and can stretch for tens of thousands of light years, creating a stunning visual spectacle. But the story of IC 3418 goes beyond its striking appearance. The process of ram pressure stripping has profound implications for the galaxy's future. Without its gas reservoir, IC 3418 is effectively being starved of the fuel it needs to form new stars. Over time, this could lead to a decline in star formation, transforming the galaxy into a red and dead system, dominated by older, cooler stars. This raises an intriguing question. How common is this process in the universe, and how does it shape the evolution of galaxies on a larger scale? Interestingly, IC 3418 also challenges some of our assumptions about galaxy evolution. While ram pressure stripping is often seen as a destructive force, it can also trigger bursts of star formation in certain regions of the galaxy. As the gas is compressed by the pressure of the cluster's environment, it can collapse and ignite the birth of new stars. This dual nature, destruction and creation, highlights the complexity of galactic interactions and underscores the importance of studying galaxies like IC 3418 in detail. Moreover, IC 3418 offers a unique opportunity to study the interplay between galaxies and their environments. By observing how the galaxy's gas is stripped and redistributed, astronomers can gain insights into the dynamics of the Virgo cluster itself. The trails of gas left behind by IC 3418 act as cosmic breadcrumbs, revealing the paths that galaxies take as they move through the cluster. This, in turn, helps us understand the larger processes that govern the evolution of galaxy clusters over billions of years. Yet, despite the wealth of information we've gathered, IC 3418 remains a mystery in many ways. Why does ram pressure stripping affect some galaxies more severely than others? What determines whether a galaxy will experience a burst of star formation or simply fade away? And how do these processes contribute to the overall structure and evolution of galaxy clusters? These questions continue to drive research, with astronomers using cutting-edge telescopes and simulations to unravel the secrets of this peculiar galaxy. As we explore IC 3418, we're reminded of the dynamic and ever-changing nature of the universe. From the dramatic effects of ram pressure stripping to the intricate dance of galaxies within clusters, this phenomenon offers a fascinating glimpse into the forces that shape our cosmic neighborhood. And with that, let's move on to another intriguing feature of the Virgo cluster, where the mysteries of the cosmos continue to unfold. Now, let's shift our gaze to another fascinating feature of the Virgo cluster, the enigmatic tidal tails. These long, sweeping streams of stars and gas are the cosmic fingerprints of gravitational interactions between galaxies, offering a window into the cluster's turbulent past. As galaxies in the Virgo cluster dance around one another, their immense gravitational forces pull and stretch material, creating these spectacular tails that can span hundreds of thousands of light years. But these tidal tails are more than just beautiful cosmic ribbons. They hold vital clues about the history and evolution of the cluster itself. Tidal tails form when galaxies come close enough to each other for their gravity to interact dramatically. Imagine two galaxies passing by one another, their gravitational fields tugging at each other like cosmic tides. This gravitational tug of war can strip stars, gas, and dust from the outer regions of the galaxies, flinging them into space and forming these elongated structures. Over time, these tails can become vast, intricate networks, weaving through the cluster and connecting galaxies in a delicate cosmic web. But what makes them so significant? For one, they serve as a record of past interactions, allowing astronomers to reconstruct the history of galaxy collisions and near misses within the cluster. One of the most striking examples of tidal tails in the Virgo cluster can be seen in the galaxy pair known as the mice galaxies. These two galaxies are locked in a slow-motion collision, their gravitational forces pulling long, luminous tails of stars and gas out into space. These tails not only reveal the intensity of the interaction, but also provide insights into the dynamics of galaxy mergers. By studying the structure and composition of these tails, astronomers can determine how much material was stripped away, how fast the galaxies are moving, and even predict their eventual fate. Will they merge into a single, larger galaxy, or will they continue their cosmic dance indefinitely? But tidal tails aren't just about the past, they also play a role in shaping the future of the Virgo cluster. The material in these tails doesn't simply disappear, it often becomes part of the intracluster medium, the diffused gas that fills the space between galaxies. This recycled material can eventually contribute to the formation of new stars or even entire galaxies, adding another layer of complexity to the cluster's evolution. In this way, tidal tails are both a product of and a contributor to the dynamic environment of the Virgo cluster. What's particularly intriguing is how tidal tails challenge our understanding of galaxy interactions. While we often think of galaxy collisions as violent, destructive events, tidal tails reveal a more nuanced picture. They show that even in the midst of chaos, there's a delicate balance between destruction and creation. The same forces that tear galaxies apart can also seed new structures, highlighting the intricate interplay of forces at work in the universe. This duality makes tidal tails a key area of study for astronomers seeking to understand the life cycle of galaxies and the evolution of galaxy clusters. Yet, despite their significance, tidal tails remain shrouded in mystery. Why do some interactions produce long, prominent tails while others result in barely noticeable features? How do the properties of the galaxies involved, such as their size, mass, and speed, affect the formation and evolution of these tails? And what role do tidal tails play in the larger context of the Virgo cluster's evolution? These questions continue to drive research, with astronomers using advanced telescopes and simulations to uncover the secrets of these cosmic streamers. As we explore the tidal tails of the Virgo cluster, we're reminded of the interconnectedness of the universe. These delicate structures, born from the gravitational dance of galaxies, tell a story of cosmic encounters that have shaped the cluster over billions of years. And with that, let's move on to another captivating phenomenon, where the mysteries of the Virgo cluster continue to unfold. Now, let's journey deeper into the heart of the Virgo cluster, where its dense core holds secrets that continue to baffle astronomers. At the center of this vast cosmic gathering lies a region of extraordinary density, teeming with galaxies, hot gas, and dark matter. This core is not just a crowded hub of activity. It's a place where the rules of physics seem to bend and where the mysteries of the universe come into sharp focus. The core of the Virgo cluster is dominated by the giant elliptical galaxy Messier 87, or M87, home to the famous supermassive black hole that made history with the first ever black hole image. But M87 is just one piece of the puzzle. Surrounding it are hundreds of other galaxies, packed so tightly that their gravitational interactions shape the very fabric of the core. This dense environment creates a gravitational well so intense that it influences the motion of galaxies far beyond the core itself, pulling them inward and shaping the cluster's overall structure. One of the most striking features of the Virgo cluster's core is its hot gas. This gas, heated to millions of degrees, emits powerful X-rays that reveal the core's dynamic and energetic nature. But here's the mystery: despite the intense heat, the gas in the core isn't cooling as quickly as scientists expect. According to current models, the gas should be cooling and condensing, leading to the formation of new stars. Yet, observations show that this isn't happening. This discrepancy, known as the cooling flow problem, has puzzled astronomers for decades and remains one of the most significant challenges in understanding galaxy clusters. Another intriguing aspect of the core is its dark matter distribution. Dark matter, the invisible substance that makes up most of the universe's mass, is thought to be concentrated in the core, creating a gravitational scaffold that holds the cluster together. But how exactly is this dark matter distributed, and how does it interact with the visible matter in the core? These questions are at the forefront of astronomical research, with scientists using techniques like gravitational lensing to map the dark matter and uncover its secrets. The core's unusual properties also extend to its galaxies. Many of the galaxies in the core are elliptical or lenticular, with little to no ongoing star formation. This is in stark contrast to spiral galaxies, which are often found in less dense regions of the cluster. Why does the core favor these types of galaxies? One theory suggests that the intense gravitational environment strips away the gas needed for star formation, leaving behind galaxies that are old, red, and relatively inactive. But this is just one piece of the puzzle, and the true story of the core's galaxy population remains an open question. What makes the Virgo cluster's core such a focal point for research is its role as a cosmic laboratory. Here, astronomers can study the interplay of gravity, dark matter, and hot gas in an environment that's both extreme and accessible. The core's proximity to Earth, relatively speaking, of course, makes it an ideal target for detailed observations, allowing scientists to test theories and refine their understanding of how galaxy clusters evolve. Yet, despite decades of study, the core continues to surprise us. From its unexpected cooling flow problem to its enigmatic dark matter distribution, the Virgo Cluster's core is a reminder of how much we still have to learn about the universe. As we peer into this dense, dynamic region, we're not just exploring the heart of a galaxy cluster, we're uncovering clues about the forces that shape the cosmos itself. And with that, let's turn our attention to another captivating mystery, where the Virgo Cluster's secrets continue to unfold. Now, shifting our gaze to the outskirts of the Virgo Cluster, we encounter a puzzle that challenges our understanding of galaxy formation on a cosmic scale. This mystery is known as the Virgo Cluster's missing satellite problem. According to our current models of cosmology, large galaxy clusters like Virgo should be surrounded by hundreds, if not thousands, of smaller satellite galaxies. These satellites are thought to be remnants of the early universe, orbiting their larger counterparts much like moons orbit a planet. Yet, when astronomers look at the Virgo Cluster, they find far fewer satellite galaxies than predicted. This discrepancy raises profound questions about the nature of dark matter, the evolution of galaxies, and the very framework of our cosmological theories. So, what exactly is causing this mismatch between prediction and observation? One possibility lies in the nature of dark matter itself. The prevailing theory, known as the cold dark matter model, suggests that dark matter particles move slowly, allowing them to clump together and form the scaffolding for galaxies. This model predicts a large number of small, dark matter halos which should host satellite galaxies. However, if these halos exist, why aren't they all visible? Some scientists propose that many of these halos simply didn't accumulate enough gas to form stars, leaving them dark and nearly invisible to our telescopes. Others suggest that the intense gravitational environment of the Virgo Cluster may have stripped away the gas from these smaller galaxies, preventing them from forming stars and rendering them undetectable. Another intriguing angle involves the role of feedback mechanisms, such as supernova explosions or active galactic nuclei, which could have heated or expelled gas from these satellite galaxies, halting star formation. This would leave them as faint, ghostly remnants, difficult to spot even with our most advanced instruments. Additionally, some researchers argue that our current methods of detecting satellite galaxies might be incomplete. Many of these galaxies could be extremely faint or located in regions of the sky that are challenging to observe, making them easy to overlook. The implications of the missing satellite problem extend far beyond the Virgo Cluster. If our understanding of dark matter or galaxy formation is flawed, it could force us to rethink some of the most fundamental aspects of cosmology. For instance, alternative dark matter models such as warm dark matter or self-interacting dark matter have been proposed to address this issue. These models suggest that dark matter particles might behave differently, potentially reducing the number of small halos and aligning predictions more closely with observations. However, these theories are still in their infancy and require further testing. What makes this phenomenon so fascinating is its connection to the larger story of the universe. The missing satellite problem isn't just about counting galaxies, it's about understanding the invisible forces that shape the cosmos. By studying the Virgo Cluster, astronomers are not only probing the mysteries of dark matter and galaxy evolution, but also testing the very foundations of our cosmological models. Each observation, each new discovery, brings us one step closer to unraveling these cosmic enigmas. As we continue to explore the Virgo Cluster, the missing satellite problem serves as a reminder of how much we still have to learn. It challenges us to refine our theories, improve our observational techniques, and remain open to new possibilities. And with that, let's turn our attention to another captivating mystery, where the Virgo Cluster's secrets continue to unfold. Now, as we venture deeper into the mysteries of the Virgo cluster, we encounter a phenomenon that seems almost otherworldly: high-velocity clouds of gas racing through the vast expanse of space. These clouds, moving at speeds that defy expectations, are not bound to any single galaxy, but instead drift freely through the cluster, leaving astronomers puzzled about their origins and their role in shaping the cosmic landscape. High-velocity clouds are immense structures of gas, often spanning thousands of light years, and they move at speeds that can reach hundreds of kilometers per second. What makes them particularly intriguing is their sheer velocity, which far exceeds the typical motion of gas within galaxies. This raises a critical question: where do these clouds come from, and what forces are propelling them at such incredible speeds? One leading theory suggests that these clouds could be remnants of galactic collisions or interactions. When galaxies collide or pass close to one another, the gravitational forces at play can strip away vast amounts of gas, flinging it into the intergalactic medium at high speeds. Over time, this gas could accumulate into the high-velocity clouds we observe today. Another possibility is that these clouds originate from the outskirts of galaxies, where supernova explosions or intense stellar winds might eject gas into the surrounding space, accelerating it to extraordinary velocities. But the mystery doesn't end there. These high-velocity clouds also play a significant role in the evolution of the Virgo cluster. As they move through the cluster, they interact with the galaxies they encounter, depositing gas and potentially triggering new waves of star formation. This process, known as gas accretion, can rejuvenate aging galaxies, providing them with the raw materials needed to form new stars and sustain their growth. However, the impact isn't always positive. In some cases, the high-speed gas can strip away a galaxy's existing gas reserves, effectively quenching star formation and leaving the galaxy to fade into obscurity. The study of these clouds also offers a unique window into the dynamics of the Virgo cluster's intergalactic medium. By analyzing their composition and motion, astronomers can gain insights into the distribution of matter within the cluster, as well as the forces that govern its evolution. For instance, the presence of high-velocity clouds suggests that the cluster is far from static. It's a dynamic, ever-changing environment where galaxies and gas are in constant motion, shaped by the interplay of gravity, pressure, and cosmic winds. Yet, despite the progress made in understanding these clouds, many questions remain unanswered. Why do some clouds move faster than others? What determines their trajectories, and how do they interact with the cluster's magnetic fields? These are just a few of the puzzles that continue to challenge scientists, driving them to refine their models and develop new observational techniques. As we ponder the enigma of high-velocity clouds, we're reminded once again of the complexity and beauty of the Virgo cluster. These clouds are not just fleeting anomalies, they are key players in the cosmic drama, shaping the fate of galaxies and offering clues to the forces that govern the universe. And with that, let's turn our attention to another captivating mystery, where the Virgo cluster's secrets continue to unfold. Now, shifting our gaze to the invisible yet omnipresent force that binds the Virgo cluster together, we delve into the enigmatic dark matter halo that envelops this cosmic neighborhood. Unlike the stars and gas we can see, dark matter remains hidden, detectable only through its gravitational influence. This mysterious substance forms a vast, diffuse halo around the cluster, extending far beyond the visible galaxies and playing a crucial role in shaping the cluster's structure and behavior. The dark matter halo is not just a passive backdrop, it's the gravitational glue that holds the Virgo cluster together. Without it, the galaxies within the cluster would fly apart, unable to maintain their collective motion. This halo's immense gravitational pull dictates the orbits of galaxies, influences their interactions, and even determines how the cluster evolves over time. But what exactly is this dark matter halo made of, and how does it exert such a profound influence? One of the most striking properties of the dark matter halo is its sheer mass. Estimates suggest that dark matter makes up roughly 85% of the cluster's total mass, far outweighing the visible matter we can observe. This dominance means that the halo's gravitational field is the primary force shaping the cluster's dynamics. Galaxies within the Virgo cluster orbit within this halo, their paths guided by its invisible contours. Even the high-velocity clouds we discussed earlier are influenced by the halo's gravitational pull, their trajectories bending as they move through this unseen landscape. But the dark matter halo's influence goes beyond just holding the cluster together. It also plays a key role in the formation and evolution of galaxies. As galaxies move through the halo, they experience tidal forces that can strip away gas and stars, altering their structure and star formation rates. In some cases, these interactions can trigger bursts of star formation, while in others, they can leave galaxies stripped and dormant. The halo's gravitational field also acts as a cosmic funnel, drawing in gas and smaller galaxies from the surrounding intergalactic medium, feeding the growth of the cluster over billions of years. Despite its importance, the dark matter halo remains one of the most elusive aspects of the Virgo cluster. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopes. Instead, astronomers rely on indirect methods to study it, such as observing the gravitational lensing effect, where the halo's mass bends the light from distant background galaxies. These observations have revealed that the halo is not uniform. It has a complex, clumpy structure, with denser regions where dark matter accumulates and sparser areas where it is less concentrated. The study of the Virgo cluster's dark matter halo also provides valuable insights into the nature of dark matter itself. While we still don't know what dark matter is made of, its behavior in the cluster offers clues. For instance, the way it clumps together suggests that dark matter particles move relatively slowly, a characteristic that aligns with the leading theory of cold dark matter. Yet, many questions remain. Why does dark matter form halos in the first place? How does it interact with ordinary matter, if at all? And what role does it play in the larger cosmic web? As we explore the dark matter halo, we're reminded of how much of the universe remains hidden from our view. This invisible structure is not just a curiosity, it's a fundamental part of the cosmic puzzle, shaping the Virgo cluster and influencing the fate of its galaxies. And as we continue our journey through the mysteries of the Virgo cluster, we'll uncover even more secrets that challenge our understanding of the cosmos. Now, as we turn our attention to another perplexing feature of the Virgo cluster, we encounter the mystery of its cooling flow, or rather, the lack thereof. At the heart of this cosmic conundrum lies a paradox. The cluster's hot gas, which should be cooling and collapsing to form new stars, seems to defy expectations. Instead of a steady stream of cooling gas fueling star formation, astronomers observe a puzzling stagnation. This phenomenon, known as the cooling flow problem, has left scientists scratching their heads and searching for answers. The Virgo cluster is filled with an immense reservoir of hot gas, heated to millions of degrees and glowing brightly in X-rays. According to basic physics, this gas should gradually lose energy, cool down, and flow inward toward the cluster's center. As it cools, it should condense into denser clouds, eventually collapsing to form new stars. This process, called a cooling flow, was once thought to be a natural and inevitable part of galaxy cluster evolution. However, observations tell a different story. The expected cooling and star formation are not happening at the rates predicted by theory. One of the most striking pieces of evidence comes from X-ray observations of the cluster's core. While the gas is indeed hot and luminous, it doesn't show the expected signs of cooling to lower temperatures. Instead, the gas seems to remain hot, as if something is preventing it from losing energy and collapsing. This discrepancy has led astronomers to question their understanding of the processes at work in galaxy clusters. What is stopping the gas from cooling? And why isn't it forming stars as expected? Several theories have been proposed to explain this puzzling behavior. One leading idea involves the supermassive black hole at the center of Messier 87, the cluster's dominant galaxy. This black hole is known to emit powerful jets of energy, which could be heating the surrounding gas and counteracting the cooling process. In this scenario, the black hole acts like a cosmic thermostat, pumping energy into the gas and preventing it from cooling too much. This feedback mechanism could explain why the gas remains hot and why star formation is suppressed. Another possibility is that turbulence and magnetic fields within the cluster are playing a role. The hot gas in the Virgo cluster is not static, it's constantly churning and swirling, stirred up by the motions of galaxies and the gravitational interactions within the cluster. This turbulence could mix the gas, redistributing heat and preventing it from cooling in localized regions. Similarly, magnetic fields threading through the gas might inhibit its ability to condense and form stars, adding another layer of complexity to the cooling flow problem. Yet, despite these theories, the cooling flow mystery remains unsolved. The interplay between heating and cooling processes in the Virgo cluster is far more intricate than initially thought, and astronomers are still working to piece together the full picture. What's clear is that the cooling flow problem challenges our understanding of how galaxy clusters evolve and how energy is transferred within them. It also highlights the delicate balance between the forces that shape the universe, from the immense gravity of dark matter to the explosive energy of black holes. As we continue to explore the Virgo cluster, the cooling flow problem serves as a reminder of how much we still have to learn about the cosmos. It's a puzzle that not only deepens our understanding of galaxy clusters, but also pushes the boundaries of astrophysics itself. And as we move forward, we'll uncover even more mysteries that challenge our assumptions and inspire new questions about the universe we inhabit. Now, shifting our gaze to another fascinating aspect of the Virgo cluster, we delve into the phenomenon of gravitational lensing, a cosmic trick of light that reveals hidden secrets about the universe. Gravitational lensing occurs when the immense gravity of a massive object, like a galaxy or cluster, bends the light from objects behind it, acting like a natural magnifying glass. In the Virgo cluster, this effect has become a powerful tool for astronomers, offering a unique window into the invisible world of dark matter. The Virgo cluster's gravitational lenses are particularly intriguing because of the cluster's sheer size and density. With hundreds of galaxies packed into a relatively small region of space, the combined gravitational pull creates a complex web of lensing effects. These distortions allow scientists to map the distribution of dark matter, the mysterious substance that makes up most of the universe's mass but doesn't emit, absorb, or reflect light. By studying how light bends around the cluster, astronomers can trace the invisible scaffolding of dark matter that holds the cluster together. One of the most remarkable examples of gravitational lensing in the Virgo cluster is the way it magnifies distant galaxies. Light from these faraway objects travels billions of light years to reach us, but as it passes through the cluster, it gets warped and stretched, creating multiple images or even arcs of light. These distorted images are not just visually stunning, they provide critical data about the mass and structure of the cluster. By analyzing the shapes and positions of these lensed images, scientists can calculate the amount and distribution of dark matter in the Virgo cluster with remarkable precision. But gravitational lensing doesn't just help us map dark matter. It also offers insights into the cluster's history and evolution. The way light bends around the cluster reveals how its mass is distributed, which in turn tells us about the gravitational interactions that have shaped it over billions of years. For instance, the presence of dark matter filaments, thread-like structures connecting galaxies, can be inferred from the patterns of lensing. These filaments are thought to play a crucial role in the growth and structure of galaxy clusters, and the Virgo cluster's lenses provide a rare opportunity to study them in detail. Moreover, gravitational lensing has practical applications beyond mapping dark matter. It can magnify distant galaxies that would otherwise be too faint to observe, allowing astronomers to study the early universe in unprecedented detail. In some cases, lensing has even revealed galaxies that existed just a few 100 million years after the Big Bang, offering a glimpse into the universe's infancy. This makes the Virgo Cluster not just a laboratory for understanding dark matter, but also a time machine that lets us peer into the distant past. Yet, despite its incredible potential, gravitational lensing is not without its challenges. The distortions caused by the cluster's gravity are often subtle and complex, requiring sophisticated models and simulations to interpret. Astronomers must account for the cluster's intricate mass distribution, the shapes of individual galaxies, and even the effects of other nearby clusters to accurately reconstruct the lensed images. It's a painstaking process, but one that yields invaluable insights into the universe's hidden architecture. As we continue to explore the Virgo Cluster, gravitational lensing remains one of the most powerful tools in our cosmic toolkit. It bridges the gap between the visible and the invisible, shedding light on the dark matter that shapes the universe and revealing the distant galaxies that lie beyond our reach. And as our understanding of this phenomenon deepens, so too does our appreciation for the intricate and interconnected nature of the cosmos. With each new discovery, we move closer to unraveling the mysteries of the Virgo Cluster and the universe itself. Now, turning our attention to another cosmic oddity within the Virgo Cluster, we encounter the peculiar galaxy NGC 4522. This galaxy stands out not for its size or brightness, but for the dramatic forces, its enduring forces that are reshaping its very structure. NGC 4522 is undergoing a process known as ram pressure stripping, a phenomenon that occurs when a galaxy moves through the dense intergalactic medium of a cluster, much like a ship cutting through turbulent waters. Ram pressure stripping happens when the hot gas between galaxies in a cluster exerts a powerful force on a galaxy as it moves. This force can strip away the galaxy's own gas, which is essential for forming new stars. In the case of NGC 4522, the effects are striking. Observations reveal long, trailing streams of gas being ripped away from the galaxy, leaving behind a ghostly wake. These streams are not just remnants of destruction, they are clues to the intense environment of the Virgo Cluster's intergalactic medium. The intergalactic medium in the Virgo Cluster is a seething sea of hot gas, with temperatures reaching millions of degrees. As NGC 4522 hurtles through this environment, the pressure from the gas is so immense that it overcomes the galaxy's own gravitational pull, stripping away its gas and dust. This process is not just destructive, it's transformative. Over time, ram pressure stripping can leave a galaxy devoid of the material needed to form new stars, effectively halting its growth and evolution. But NGC 4522 is more than just a victim of cosmic forces. It's also a window into the dynamics of the Virgo Cluster. By studying the galaxy's interaction with the intergalactic medium, astronomers can learn about the density and behavior of the gas that fills the cluster. The trails of gas left behind by NGC 4522 act as markers, tracing the flow of the intergalactic medium and revealing how it shapes the galaxies within the cluster. What makes NGC 4522 particularly fascinating is the speed at which this process is occurring. The galaxy is moving through the cluster at an astonishing velocity, which amplifies the effects of ram pressure stripping. This rapid motion creates a stark contrast between the galaxy's core, which remains relatively intact, and its outer regions, which are being torn apart. This disparity offers a unique opportunity to study how different parts of a galaxy respond to extreme environmental pressures. Moreover, NGC 4522 provides insights into the life cycle of galaxies in dense clusters. As galaxies like this one lose their gas, they transition from being star-forming spirals to quiescent ellipticals. This transformation is a key part of the evolution of galaxy clusters, and NGC 4522 is a prime example of this process in action. By observing its gradual transformation, astronomers can piece together the story of how galaxies in the Virgo cluster have evolved over billions of years. Yet, despite the destructive nature of RAM pressure stripping, it's not the end of the road for NGC 4522. The galaxy's core remains resilient, and its remaining gas could still give rise to new stars, albeit at a much slower rate. This resilience highlights the complex interplay between destruction and creation in the cosmos, reminding us that even in the harshest environments, life, or in this case, starlight, finds a way to endure. As we continue to study NGC 4522, it serves as a vivid reminder of the dynamic and often violent processes that shape the universe. Its story is one of transformation, resilience, and the relentless forces that govern the cosmos. And as we unravel the mysteries of this strange galaxy, we gain a deeper understanding of the Virgo cluster and the intricate dance of galaxies within it. Now, shifting our focus to another enigmatic aspect of the Virgo cluster, we delve into the mysterious world of cosmic rays. These high-energy particles, traveling at nearly the speed of light, are one of the most intriguing phenomena in the universe. But what exactly are cosmic rays, and where do they come from? Within the Virgo cluster, their origins and behavior present a fascinating puzzle for astronomers. Cosmic rays are not rays in the traditional sense. They are actually charged particles, such as protons and atomic nuclei, accelerated to incredible speeds. While some cosmic rays originate from our own sun, the most energetic ones come from far beyond our solar system, often from violent events like supernova explosions or the powerful jets emitted by supermassive black holes. In the Virgo cluster, the dense environment and the presence of numerous galaxies make it a hotspot for these high-energy particles. One of the key questions surrounding cosmic rays in the Virgo cluster is how they are accelerated to such extreme energies. The cluster's turbulent environment, filled with shock waves and magnetic fields, provides the perfect conditions for particle acceleration. As galaxies collide and black holes spew out jets of material, these events create shock waves that can propel particles to nearly the speed of light. The result is a constant stream of cosmic rays permeating the cluster. But cosmic rays don't just travel through space unnoticed, they interact with their surroundings in profound ways. When these high-energy particles collide with the gas and dust in the cluster, they produce secondary particles and radiation, including gamma rays. This interaction not only heats the surrounding gas but also contributes to the overall energy balance of the cluster. In fact, cosmic rays are thought to play a significant role in shaping the thermal and magnetic properties of the Virgo cluster's intergalactic medium. Another intriguing aspect of cosmic rays is their ability to influence star formation. When cosmic rays interact with molecular clouds, dense regions of gas where stars are born, they can ionize the gas, altering its chemistry and dynamics. This process can either trigger or suppress star formation, depending on the conditions. In the Virgo cluster, where galaxies are constantly interacting and evolving, cosmic rays add another layer of complexity to the already dynamic environment. Despite their importance, cosmic rays are notoriously difficult to study. Because they are charged particles, their paths are bent by magnetic fields, making it challenging to trace their origins. However, by observing the gamma rays and other secondary particles they produce, astronomers can piece together their behavior and impact. The Virgo cluster, with its rich array of galaxies and energetic events, offers a unique laboratory for studying these elusive particles. What makes cosmic rays in the Virgo cluster particularly fascinating is their potential to reveal the hidden workings of the universe. By studying how these particles are produced, accelerated, and interact with their environment, scientists can gain insights into some of the most extreme processes in the cosmos. From the violent deaths of massive stars to the powerful jets of supermassive black holes, cosmic rays provide a window into the high-energy universe. As we continue to explore the Virgo cluster, cosmic rays remind us of the unseen forces that shape the cosmos. Their presence is a testament to the dynamic and interconnected nature of the universe, where even the smallest particles can have a profound impact. And as we unravel the mysteries of these high-energy travelers, we come one step closer to understanding the intricate dance of matter and energy that defines the Virgo cluster and the universe as a whole. Now, turning our attention to another layer of the Virgo cluster's mysteries, we encounter the enigmatic magnetic fields that weave through its vast expanse. These invisible forces, though unseen, play a crucial role in shaping the behavior and evolution of galaxies within the cluster. But what exactly are these magnetic fields, and how do they come to exist in such a complex cosmic environment? Magnetic fields in the Virgo cluster are not uniform. They vary in strength and direction, creating a tangled web of forces that stretch across millions of light years. These fields are thought to originate from a combination of processes, including the motion of charged particles, the turbulence of intergalactic gas, and the powerful jets emitted by supermassive black holes. As galaxies move and interact within the cluster, their magnetic fields can become amplified and twisted, adding to the complexity of the overall structure. One of the most fascinating aspects of these magnetic fields is their ability to influence the evolution of galaxies. For instance, they can affect the movement of gas within galaxies, either compressing it to trigger star formation or dispersing it to slow down the process. In the Virgo cluster, where galaxies are constantly interacting and merging, magnetic fields add another layer of complexity to these dynamic processes. They can also shape the behavior of cosmic rays, guiding their paths and influencing how they interact with the surrounding gas and dust. But how do astronomers study these invisible forces? One method involves observing the polarization of light emitted by galaxies and the cluster's hot gas. When light passes through a magnetic field, its waves become aligned in a specific direction, a phenomenon known as polarization. By measuring this alignment, scientists can map the strength and orientation of magnetic fields across the cluster. Another approach is to study the synchrotron radiation emitted by high-energy electrons spiraling around magnetic field lines. This radiation provides clues about the field's intensity and distribution. The presence of magnetic fields also has implications for the cluster's large-scale structure. They can help regulate the flow of gas between galaxies, influencing the formation of galaxy clusters and superclusters. In the Virgo cluster, magnetic fields are thought to play a role in shaping the intracluster medium, the hot gas that fills the space between galaxies. By affecting the motion and temperature of this gas, magnetic fields contribute to the overall energy balance and dynamics of the cluster. Despite their importance, the origins and evolution of these magnetic fields remain a subject of intense debate. Some theories suggest that they were present in the early universe, amplified over time by the motion of galaxies and the growth of cosmic structures. Others propose that they are generated locally through processes like turbulence and the activity of supermassive black holes. Understanding the true nature of these fields could provide valuable insights into the formation and evolution of the Virgo cluster and the universe as a whole. As we continue to explore the Virgo cluster, magnetic fields remind us of the unseen forces that shape the cosmos. Their intricate interplay with galaxies, gas, and cosmic rays highlights the interconnected nature of the universe. And as we unravel the mysteries of these invisible threads, we gain a deeper appreciation for the complex tapestry of matter and energy that defines the Virgo cluster and the broader cosmos. With this in mind, let's now shift our focus to another intriguing phenomenon, the missing globular clusters in the Virgo cluster, and what their absence might tell us about the cluster's history and evolution. Now, as we delve into another layer of the Virgo cluster's mysteries, we encounter a puzzling phenomenon, the missing globular clusters. These dense, spherical collections of stars are typically found orbiting galaxies, acting as ancient relics of the universe's early days. Yet, in the Virgo cluster, something unusual is happening. There are far fewer globular clusters than scientists expect. This discrepancy raises intriguing questions about the cluster's history and the forces shaping its evolution. Globular clusters are like cosmic time capsules containing some of the oldest stars in the universe. They are thought to form during the early stages of galaxy formation, making them invaluable for understanding the origins of galaxies and their environments. In most galaxy clusters, including our own Milky Way, globular clusters are abundant. However, in the Virgo cluster, the number of observed globular clusters falls significantly short of predictions based on current models of galaxy formation and evolution. One possible explanation for this shortage lies in the cluster's dynamic environment. The Virgo cluster is a bustling hub of gravitational interactions where galaxies frequently collide and merge. These violent encounters can strip globular clusters from their host galaxies, scattering them into the vast intergalactic space. Over time, some of these clusters may dissolve or be absorbed by other galaxies, reducing their overall numbers. Additionally, the intense gravitational forces within the cluster could disrupt the formation of new globular clusters, further contributing to their scarcity. Another factor to consider is the role of dark matter. Globular clusters are often found in regions with high concentrations of dark matter, which helps bind them together. If the distribution of dark matter in the Virgo cluster is uneven or less concentrated than expected, it could explain why fewer globular clusters have formed or survived. This idea ties into the broader mystery of dark matter's influence on galaxy clusters and their evolution. The missing globular clusters also have implications for our understanding of the Virgo cluster's history. If the cluster experienced a period of intense galaxy interactions earlier in its life, it could have led to the destruction or dispersal of many globular clusters. Alternatively, the cluster's unique environment might have prevented the formation of these clusters in the first place. Either scenario challenges our current theories about how globular clusters form and persist over cosmic time. To study this phenomenon, astronomers rely on advanced telescopes and observational techniques. By mapping the distribution of globular clusters within the Virgo cluster, scientists can identify patterns that reveal the forces at play. For example, if globular clusters are found predominantly in certain regions, it could indicate areas where gravitational interactions are less intense or where dark matter is more concentrated. These observations help refine our models of galaxy cluster formation and shed light on the processes that shape the universe. The mystery of the missing globular clusters is more than just a cosmic curiosity. It's a window into the complex interplay of forces that govern the Virgo cluster. By unraveling this puzzle, we gain deeper insights into the cluster's past, present, and future. And as we continue to explore, we're reminded that even the smallest cosmic details can hold profound implications for our understanding of the universe. With this in mind, let's now turn our attention to another fascinating aspect of the Virgo cluster: the unusually low star formation rates observed in its galaxies and what this tells us about the cluster's evolution. Now, shifting our gaze to another intriguing mystery, we find ourselves examining the Virgo cluster's puzzlingly low star formation rates. Unlike many other regions of the universe where galaxies are bustling with the birth of new stars, the galaxies within the Virgo cluster seem to be in a state of cosmic hibernation. This phenomenon raises critical questions about what stifles star formation in such a dense and dynamic environment. Star formation is a fundamental process in the life cycle of galaxies, driven by the collapse of gas clouds under gravity. In most galaxies, this process is ongoing, leading to the creation of new stars that light up the cosmos. However, in the Virgo cluster, something is suppressing this activity. One of the primary culprits is the cluster's harsh environment. The space between galaxies in the Virgo cluster is filled with hot, ionized gas known as the intracluster medium. This gas, heated to millions of degrees, acts as a barrier, preventing the cooler gas within galaxies from collapsing and forming stars. Another factor contributing to the low star formation rates is the process known as ram pressure stripping. As galaxies move through the cluster at high speeds, they encounter the dense intracluster medium, which can strip away their gas reservoirs. Without sufficient gas, galaxies lose the raw material needed to create new stars. This process is particularly evident in spiral galaxies, which are rich in gas but vulnerable to such stripping. Over time, these galaxies can transform into gas-poor ellipticals, further reducing star formation activity. Gravitational interactions between galaxies also play a significant role. The Virgo cluster is a crowded place with galaxies frequently passing close to one another. These close encounters can trigger tidal forces that disrupt the internal structure of galaxies, redistributing their gas and making it harder for star formation to occur. In some cases, these interactions can even lead to galaxy mergers, which, while dramatic, often result in a temporary burst of star formation followed by a long period of quiescence. Interestingly, the cluster's central regions, where galaxies are most densely packed, show the lowest star formation rates. This suggests that the combined effects of the intracluster medium, ram pressure stripping, and gravitational interactions are most intense in these areas. However, even in the outskirts of the cluster, where conditions are less extreme, star formation rates remain lower than expected. This indicates that the suppression of star formation is a cluster-wide phenomenon, influenced by both local and large-scale factors. The implications of this low star formation extend beyond the Virgo cluster itself. Understanding why star formation is suppressed in such environments can shed light on the evolution of galaxies in other dense regions of the universe. It also challenges our current models of galaxy formation and evolution, which often assume a more active role for star formation in galaxy clusters. By studying the Virgo cluster, astronomers can refine these models and gain a clearer picture of how galaxies evolve in different cosmic environments. To investigate this phenomenon, scientists use a combination of observations and simulations. Telescopes like the Hubble Space Telescope and the Atacama Large Millimeter Array provide detailed views of the gas and star-forming regions within the cluster's galaxies. Meanwhile, computer simulations help researchers model the complex interactions between galaxies and their environment, offering insights into the processes that suppress star formation. The enigma of the Virgo cluster's low star formation rates is a reminder of how interconnected the universe's processes are. From the hot intracluster medium to the gravitational dance of galaxies, every element plays a role in shaping the cosmic landscape. As we continue to explore this phenomenon, we uncover not just the secrets of the Virgo cluster, but also the broader story of how galaxies live, evolve, and sometimes fade into cosmic silence. With this in mind, let's now turn to the final mystery in our journey through the Virgo cluster, its predicted future evolution and what it reveals about the ultimate fate of galaxy clusters in the universe. As we near the end of our exploration of the Virgo cluster's mysteries, we arrive at a question that looks not just to the present but to the distant future. What lies ahead for this colossal assembly of galaxies? The Virgo cluster's future evolution is a topic that combines the forces of gravity, dark matter, and the relentless passage of time, offering a glimpse into the ultimate fate of galaxy clusters in the universe. One of the most dramatic processes shaping the Virgo cluster's future is galaxy mergers. In a cluster as densely packed as Virgo, galaxies are constantly drawn together by gravity. Over billions of years, these close encounters will lead to collisions and mergers, transforming the cluster's structure. When two galaxies merge, their stars and gas clouds collide, often triggering bursts of star formation. However, these bursts are typically short-lived, as the merger process disrupts the galaxy's gas reservoirs, eventually leaving behind a larger, more massive galaxy. Over time, these mergers will reduce the number of smaller galaxies in the cluster, creating a population of giant elliptical galaxies at its core. Dark matter, the invisible scaffolding of the universe, also plays a crucial role in shaping the Virgo cluster's future. The cluster's immense dark matter halo exerts a powerful gravitational pull, influencing the motion of galaxies within it. As galaxies orbit the cluster's center, they interact with this dark matter, which can alter their paths and speeds. These interactions can lead to further mergers or even eject galaxies from the cluster entirely, sending them hurtling into intergalactic space. At the same time, dark matter's gravitational influence helps maintain the cluster's overall structure, ensuring that it remains a cohesive entity even as individual galaxies evolve. Another key factor in the Virgo cluster's future is the continued expansion of the universe. While gravity binds the cluster together on a local scale, the universe's expansion exerts a counterforce, pulling galaxies apart on larger scales. Over time, this expansion will cause the Virgo cluster to grow more isolated as the space between it and other galaxy clusters increases. However, within the cluster itself, gravity will continue to dominate, driving the ongoing processes of galaxy mergers and interactions. The ultimate fate of the Virgo cluster is tied to the fate of the universe itself. In a scenario where dark energy continues to accelerate the universe's expansion, the cluster will eventually become an island in an ever-expanding cosmic ocean. Galaxies within the cluster will continue to merge and evolve, but new star formation will gradually decline as gas reservoirs are depleted. Over trillions of years, the Virgo cluster may become a quiet, aging collection of galaxies with little activity beyond the occasional merger of its remaining giants. Studying the Virgo cluster's future evolution not only helps us understand the destiny of galaxy clusters, but also provides insights into the broader workings of the universe. By observing the processes at play in Virgo, astronomers can refine their models of galaxy formation and evolution, shedding light on how structures like this come to be and how they change over time. The Virgo cluster serves as a cosmic laboratory, offering a window into the forces that shape the universe on the largest scales. As we conclude our journey through the Virgo cluster's mysteries, we're reminded of the dynamic and ever-changing nature of the cosmos. From the birth of stars to the collision of galaxies, the universe is a place of constant transformation. The Virgo cluster, with its rich tapestry of phenomena, stands as a testament to the complexity and beauty of the cosmos, inviting us to continue exploring its secrets and uncovering the stories written in the stars. As we bring our journey through the Virgo cluster to a close, it's worth reflecting on the incredible mysteries we've uncovered. From galaxies that defy our understanding of dark matter to supermassive black holes that challenge the limits of physics, the Virgo cluster is a treasure trove of cosmic enigmas. Each of these 25 unexplained phenomena offers a unique puzzle, pushing scientists to rethink what we know about the universe and inspiring us to ask even bigger questions. These mysteries aren't just fascinating curiosities, they're keys to unlocking the secrets of the cosmos. By studying the Virgo cluster, astronomers gain insights into the forces that shape galaxies, the behavior of dark matter, and the evolution of the universe itself. Every discovery, every unanswered question, brings us one step closer to understanding the grand tapestry of existence, but the story doesn't end here. The Virgo cluster continues to surprise us, and there's still so much to explore. What do you think lies at the heart of these mysteries? Do you have a theory about the missing dark matter, the strange behavior of ultra-diffused galaxies, or the future of the cluster itself? Share your thoughts in the comments below. We'd love to hear your ideas and spark a conversation about the wonders of the universe. If you enjoyed this deep dive into the Virgo Cluster's mysteries, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. The universe is full of secrets waiting to be uncovered, and we're just getting started. Thanks for joining us on this cosmic adventure. Until next time, keep looking up.